Let's review galvanic or voltaic cells. In a galvanic cell, the reaction is spontaneous, which means that the change in the Gibbs free energy, delta G, is negative. What we have are two electrodes in solutions connected by some device. What happens in one half cell is oxidation, where the electrode is oxidized, that is, it loses electrons. In the other half cell, we have the reduction reaction, with the electrode being called the cathode. And what happens in the reduction half cell is that ions from the solution gain electrons that are coming from the anode and played out as solid metal onto the cathode. So over time, the anode, which is this metal, is going to become less massive as its metal atoms dissolve into metal ions. Over time, typically the cathode is going to increase in mass as the ions from the solution played out as atoms onto the cathode. And what we're after in a galvanic or a voltaic cell is that electron flow. We're after the current. If D has a very low resistance, then it's a wire or an ammeter. If it has a higher resistance, then it's a device to be powered, or it's a voltmeter. In order to make this system run continuously, we also need to connect the solutions by a salt bridge or a porous disc. This allows the charge to be maintained so that we don't have too much positive or too much negative charge building up in one half cell or the other, and thereby stopping the reaction. Here is an example of a galvanic cell. Notice I've just shown the salt bridge, I haven't shown the porous disc. You don't have to have both, you have one or the other. Just for simplicity, I've shown a salt bridge. And the salt bridge has in it an electrolyte, typically in some kind of a gel, that allows ions to transfer from the salt bridge into the solutions such that the charge is maintained. What's happening here on the anode side is that we're getting more positive charge being put into the solution. So from the salt bridge, the negative ions, perhaps nitrate ions, are going to be dissolving into the solution to maintain a neutral charge in the anode compartment. Similarly, you can see on the cathode side, the amount of positive charge is decreasing. We're taking positive charge out of the solution, and so we need to replenish it with cations from the salt bridge, perhaps potassium ions or sodium ions. The oxidized thing and the reduced thing are not in direct contact. So we use wires to connect them, and then we use the current that's produced. This is what we're doing in a galvanic cell. With a galvanic cell, D, which is a device, never contributes energy. It always consumes energy, or at the very least simply transfers energy, but it never adds any energy into the system. If it's a wire, or if it's an ammeter or a voltmeter or some device to be powered, whatever D is, it doesn't add any energy into the system. The electrodes are connected by wires of some kind, and the solutions are connected by a salt bridge or a porous disc. And the most familiar galvanic or voltaic cells are batteries. In a galvanic cell, we can think of the potential energy of the anode's electrons as being higher than the potential energy of the cathode's electrons. In other words, electrons are flowing from the anode towards the cathode, so we can think of the electrons as having more potential energy on the anode side. Here is a cross-section of an alkaline battery. We have here in the middle this large mass the zinc anode. And when we say zinc is an anode, that must mean that it is oxidized. And sure enough, here is the half reaction where zinc is being oxidized. You can see that this takes place in a basic medium. We also have manganese oxide cathode, or I would say manganese dioxide, but in any case. And that is where the reduction occurs. So clearly the manganese dioxide must be gaining electrons, and sure enough, there it is. The number of electrons lost equals the number of electrons gained. It turns out that the hydroxide ions also cancel here, and the water cancels as well. Our overall reaction involves zinc being oxidized and manganese dioxide being reduced, and typically on the product side we're going to have zinc oxide and something like manganese 3 oxide as a product.